Thank you for visiting bioreactorsciences.com. This presentation compares our packed bed systems, the TideCell or BellaCell, with other bioreactor systems for virus production. Currently, the four most popular bioreactor systems are roller bottles, New Brunswick's packed bed system, mechanically agitated microcarrier, and our TideCell BellaCell system. The following slides will highlight the features of each of these systems. While the roller bottle system is the simplest and most widely used system, it is very labor-intensive and requires a large physical footprint, typically in the form of clean rooms. Other than temperature, the roller bottle system cannot control pH, DO, or any other parameters. New Brunswick's packed bed system incorporates their own PET-based carrier, the FiberCell. This system utilizes agitation to circulate the media through the FiberCell matrix basket. In terms of scalability, the depth of the bed in this system becomes a limiting factor. Mechanically agitated microcarrier systems use a range of microcarriers like GE's Cytodex, Purcell's Cultisphere, and Solo Hill's polystyrene-based carrier. These bioreactor systems require agitation to keep the microcarriers in suspension, which creates shear stress, negatively impacting cell attachment to the microcarriers. Our TideCell packed bed bioreactor also uses macroporous, non-woven fibrous carriers, namely our BioNoc 2 carrier. The TideCell also utilizes the simple principle of roller bottles, mimicking the same gentle motion found in roller bottles where the cells are intermittently submerged in nutrient-rich media and exposed to air. While elementary, this principle creates an ideal environment for cell culture where there are no oxygen transfer limitations, low shear stress, and no foaming. The following slides will compare the systems based on fundamental process requirements. Because virus strains and host cell lines differ in characteristics, processes for virus production will inherently differ. Considerations for these process requirements exist in both upstream and downstream procedures, including cell propagation, cell attachment, virus infection, cell harvesting, and product recovery. For convenient propagation of adherent cells in a large-scale system, our TideCell bioreactor allows for propagation of cells from smaller to larger bioreactors with its closed, automatic harvest system. For effective and efficient cell attachment, the TideCell's relatively static seating protocol and adjustable carrier-to-media volume ratio facilitates efficient attachment under high cell concentrations. In systems like the microcarrier system, the dynamic state created by agitation reduces cell attachment efficiency, especially in large-scale systems. Cell attachment is challenged in roller bottle systems if serum-free media is used or if there are time constraints. The perfusion or exchange of fresh media during cell culture is made possible in the TideCell system because the cells are attached to carriers and immobilized in a fixed bed. The perfusion of media is straightforward and will not damage or lose cells. Retaining cells in a microcarrier system requires filtration, centrifugation, or other costly means which are not reliable and lack scalability. Additionally, the cells may be damaged during the recovery process. Similar to the prior process requirement, the TideCell is capable of perfusion or harvesting product from culture media in continuous mode with its fixed bed occupied with porous carriers. The use of filtration and/or centrifugation makes it difficult for microcarrier systems to harvest cells. The TideCell system allows for intermittent harvesting of product in semi-batch mode with no interruption to the cell culture process. This is possible with its separated matrix and media mixing vessels. For microcarrier systems to achieve this, agitation must be halted so that the microcarrier beads can settle to the bottom. This may require great lengths of time, eventually drowning the cells, especially in large systems. The TideCell has the ability to adjust the carrier-to-media volume ratio, which facilitates process optimization, leading to increased cell attachment or virus infection efficiency. In microcarrier systems, the density of microcarriers is usually fixed. Lowering carrier density reduces cell attachment rate, and conversely, increasing carrier density will require higher agitation to keep the microcarriers in suspension. This will lead to higher shear stress, lowering the growth rate. In order to control cell growth, the Tide cell is capable of controlling nutrient supply by independently removing the culture media from the cells. Other systems are challenged in being able to control nutrient supply. Rather, they can simply only reduce the nutrient feed rate. In the ever-present search for identifying methods of reducing space and labor, the TideCell fixed bed can reach up to 1 to 6 times 10 to the 7th cells per milliliter. Increasing cell density in microcarrier systems is difficult due to a few reasons, including the need for filtration or centrifugation to separate the cells from the media, and due to the limitations of microcarrier or bead density, which relates to the drawbacks of mixing shear force. Determining cell count for multiplicity of infection, or MOI, and observing CPE are critical to a successful cell culture. Having carriers of known surface area and knowing the number of carriers in a matrix vessel, the Tide cell is capable of easy sampling, enabling convenient cell count and observation of the cells on carriers. Due to limited sampling conditions in other packed bed systems, cell density is difficult to measure. Sampling in microcarrier systems, however, is feasible. Outlined in slides 9 and 13, to increase virus infection rate or transfection efficiency, the Tide cell's media volume can be adjusted relative to the matrix volume. The ratio of carrier to media volume cannot be altered in other systems, because this would result in the dilution of infection and transfection materials in the system. The media can be completely refreshed before virus infection in the Tide cell. With this feature, the titer will therefore greatly increase due to high cell density and ample nutrients. Citing the previous similar cause, the difficulty of separating the beads from media poses a challenge in replacing fresh media prior to infection in microcarrier systems. Overfoaming in the cell culture vessel is a common issue from introducing oxygen bubbles into the liquid phase. While the use of anti-foaming agents may be considered as a resolution, this agent may be toxic to some cells. Aeration in the Tide cell is facilitated through surface aeration, therefore pure oxygen or anti-foaming agents are not required, resulting in no foaming. To protect the cells, a low shear stress environment may be required, especially during the cell culture or during the post-infection period. The cells in the Tide cell are protected by the porous BioNOC2 carriers within its inherent low shear stress surroundings. In other systems where shear stress is produced from agitation, cells may become easily detached during the post-infection period, especially with no exterior protection. Scaling up with the Tide cell system is made possible due to its mass transfer capability being independent of its physical size. In roller bottle systems, increasing the number of bottles results in increased labor and required space. In a fixed bed bioreactor, nutrient limitations in the greater depths of the packed bed make scaling up a challenge, limiting it to no more than 100 liters. The Tide cell's fixed bed has the capacity to grow cells up to 5 times 10 to the 12th. This is equivalent to the capacity of a 1,000 to 4,000 liter stirred tank system. Single-use agitated tank bioreactors have scale-up limitations due to the strength of their plastic bags. Other packed bed systems cannot be scaled up beyond 100 liters due to the bed height. The Tide cell has the ability to be used completely as a single-use or hybrid system. Other systems have the same capability, although there is limited flexibility in other packed bed systems. For example, New Brunswick's Celogen Blue cannot utilize plastic vessels over 20 liters. The cells in the Tide cell will remain trapped inside the matrices of the carrier without being flushed into the harvested media even after cells are lysed after virus infection. In other systems, host cell lines protein and nucleic acids are released, which will require additional steps for removal. Cell harvesting in the TideCell is achieved with reduced space, labor, and operation costs due to its reduced working volume. The TideCell's matrix vessel containing the cells can also be separated from the mixing tank, enabling cell harvest in an automated closed system or conducted as a freeze and thaw process. Harvesting cells in a microcarrier system poses challenges that include separating the cells from the microcarriers by some extraneous means. This results in cell loss and additional washing steps, which ultimately lowers recovery rate and increases recovery costs. Harvesting cells in a roller bottle system requires intense labor due to the sheer number of bottles which need to be individually addressed. In other packed bed systems, harvesting is difficult and freezing and thawing is not feasible because the matrix cannot be aseptically removed. Similar to the previous slides, the harvesting of whole cells for encapsulated viruses can be achieved in the TideCell with its automatic integrated system and easy separation of carriers from the media. The same challenges outlined in the previous slides also makes harvesting whole cells difficult in other systems. Compared to other commonly used systems, there are many features that contribute to the TideCell's unique advantages for virus production. Operating under the same principle of roller bottles, the TideCell creates an exemplary environment for cell culture, administering maximum oxygen transfer capability, linear scale-up capability, no foaming, and extremely low shear stress. The TideCell's fixed bed allows for convenient cell separation, media exchange, and low host cell protein and DNA impurities. The ability to adjust the ratio of carrier to media volume improves cell attachment and virus infection efficiency. Lastly, the sampling capability and system use flexibility complete the TideCell's innovative offerings for successful cell culture and virus production.